When we talk about the cloud, or the massive expansion of artificial intelligence, we usually picture a boundless digital space, a sleek, ethereal void with infinite capacity to process, store, and scale our data. But the internet is not a cloud. It is a highly constrained physical machine built out of the dirt under our feet. Every processor, memory module, and fiber optic cable requires extracting specific, finite raw materials from the earth. Right now, IT leaders were slamming into the limits of that physical machine. The cost of random access memory, or RAM, the short-term memory servers use to process active tasks, is spiking by up to 90%. Lead times for critical networking components have stretched to 9 months. The natural reaction to these market spikes is to pause. Many organizations are delaying their infrastructure upgrades, assuming they can simply wait until prices normalize or manufacturers finish building new fabrication plants. You cannot engineer your way out of geology. Ignoring the physical limits of the Earth creates a massive hidden liability tail, a growing accumulation of technical debt and physical risk that threatens to crash data centers across the entire tech sector. Between 70 and 90% of the world's high-purity quartz, or HPQ, is mined from a single, unreplicable geological anomaly in Spruce Pine, North Carolina. To manufacture the silicon wafers that eventually become microchips, you have to melt raw silicon at over 1400 degrees Celsius. If the crucible holding that molten metal contains even microscopic impurities, the silicon is ruined. Manufacturers absolutely require this specific 99.99% pure fused silica from spruce pine to make the crucibles. Now, the global explosion in solar photovoltaic manufacturing is aggressively devouring that exact same supply of high-purity quartz to build solar panels. This puts the advanced semiconductor industry in a direct, zero-sum bidding war with the green energy sector. Both industries are fighting for the exact same foundational raw dirt, and there is no substitute. Because of this extreme geographical and material constraint, a permanent physical risk floor now sits underneath the hardware market. For the rest of the decade, the speed of digital expansion will be strictly capped by the scarcity of these raw materials. With raw silicon wafers in short supply, manufacturers are forced to make hard choices. They are diverting their limited production capacity away from standard components and toward their highest margin products. Today, wafer capacity is monopolized by high bandwidth memory, or HBM, the specialized memory required to build AI accelerators. This intentional shift is actively starving supply lines for standard DDR4 and DDR5 memory and enterprise solid-state drives. As a result, major cloud providers are facing surging hardware costs, and they pass those increases directly to their customers. To regain control of their budgets, many enterprises are initiating repatriation, pulling their workloads out of the cloud and moving them back to physical, on-premise servers. But executing a physical migration during a severe component shortage creates a dangerous trap. If IT teams are forced to buy high-end, multi-core servers simply because they are the only machines left in stock, they often trigger core-based software licensing inflation and rigid vendor lock-in that drains their budget for years. Organizations are being pushed to double down on physical, on-premise infrastructure at the exact historical moment that the required hardware is at its absolute most expensive and scarce. Even if an IT team successfully procures those expensive servers and installs them, they face a localized risk. They usually rely on a standard commercial building generator to protect their multi-million-dollar investment from utility outages. The problem is electrical physics. Most commercial generators produce what is known as dirty, class G1 or G2 power. While utility power is a rock-solid 60 Hz, a building generator's frequency constantly drifts, surging and jittering as heavy equipment turns on and off. A standard line interactive, uninterruptible power supply, the backup battery unit sitting in the server rack, has a very narrow window for safe frequency. When utility power fails and the generator takes over, the UPS detects that erratic frequency drift, declares the generator's power unsafe, and flatly refuses to synchronize. This triggers a battery death spiral. Because the UPS rejects incoming electricity, it relies entirely on its internal battery to keep servers running. 15 minutes later, the battery hits zero and the rack goes dark, despite the generator running perfectly right outside the building. This is a chart showing server power consumption over time, comparing idle average wattage against a GPU-heavy operation. Notice the massive peak on the graph. When power is restored to modern AI servers, their heavy graphics processing units pull a violent peak in rush current that will instantly overwhelm and trip older backup systems trying to bring the rack back online. Willful blindness to the physics of power handoffs turns a massive, tightly budgeted IT investment into an uninsurable operational failure. Surviving this tech squeeze requires a complete strategic shift. IT leaders must abandon wait-and-see budgeting and start treating their infrastructure as an exercise in active physical risk management. First, organizations must immunize the rack. This means upgrading to online double-conversion UPS systems. Unlike older models, these units digitally regenerate a perfect sine wave from scratch, making them completely impervious to the dirty power produced by building generators. Second, prioritize agility over brand. In a constrained market, rigid vendor lock-in is an operational liability. The safest and most effective play is to pivot to whatever qualified hardware is physically in stock today, regardless of the logo stamped on the bezel. This is a power audit and maintenance log tracking UPS equipment health. Documenting battery replacement schedules and physically verifying load tests are absolute necessities to prove compliance and maintain coverage during an insurance audit. The digital future promises infinite scale, but out in the real world, our capacity to compute, store, and connect will always be bound by the finite limits of dirt, copper, and perfect sine waves. Respecting those limits is the only way to keep the servers running.